This is your presenter Asloob Mudassar, and I am presenting slide number 25 of the course on laser physics. Question is, derive the Rayleigh genes and Planck radiation formulas. What is the significance of Planck formula? Answer. In order to account the distribution of radiation from black bodies, two attempts are historically important, one by Rayleigh genes and the other by Planck. In both attempts, we obtain a formula for the energy density distribution emitted by black bodies. First, the Rayleigh genes approach is described. The energy density rho nu and the average energy contained in each mode represented by E average are connected through the relationship. Rho nu is equal to P nu multiplied by E average, where P nu is the number of modes per unit volume per unit frequency range as given by equation 24.13. According to the Boltzmann statistic, the energy of a mode to be in the range E and E plus delta E has a probability of the order of C into e to the power minus E over kT multiplied by dE, where the constant C is determined through the normalization condition given by integral from 0 to infinity C, and the integrand is C e to the power minus E over kT multiplied by dE, and that is equal to 1. The average energy of a mode is given by average energy E is equal to, in the numerator we have integral of e to the power minus E over kT into dE, and divided by the denominator, which is integral from 0 to infinity e to the power minus E over kT into dE, as given in equation number 25.2. By parts integration of the denominator is worked out below. So we have the integral of the denominator from 0 to infinity e to the power minus capital E over kT and the integration is with respect to dE. So you see that these are the steps of the by parts integration that we have given. And the last step of the integration is 1 over kT multiplied by the integral from 0 to infinity E into e to the power minus E over kT into dE. So if we replace the denominator of equation 25.2 by its integral values, then you see that the integral in the numerator is cancelled out with the integral in the denominator, and we are left with kT. So the average energy will be equal to kT, as given in equation number 25.3. So we have calculated the average energy over here, and then we have also calculated PV in the previous slide, that is in equation number 24.13. So the value from the previous equation is, substituting that value over here, then we can write rho nu by substituting the value of P nu and also the value of delta and the value of the average value of energy that we just calculated. Substituting these values, we get rho nu is equal to 8 pi nu square over Cn cube into kT, where Cn is the speed of a mode in the cavity. And you know that rho nu, so let me recall that energy density, rho nu represents energy density, and P nu represents the energy density, and and P nu, you know, that is the number of modes per unit volume per unit frequency range. So we have calculated the energy density rho nu, which is given by equation 25.4. This is known as the Rayleigh genes radiation formula. So this is the Rayleigh genes radiation formula. This is incorrect, as it could not explain the radiation curves of a black body. The energy density rho is related to the spectral energy density rho nu through the relationship. So we are going to correlate the energy density rho with the spectral energy density through this integral, and the integration is over all the frequencies, which implies an infinite energy density, will exist in black body, which is incorrect. Thus the equation 25.4 and equation 25.2 are incorrect. So this equation is incorrect, and this equation, that is equation number 2, these two equations are incorrect. Next we discuss Planck radiation formula. Planck's hypothesis was that the permitted values of energy for a mode were integral multiple of a fundamental frequency h nu. Let me repeat. Permitted values of energy for a mode were integral multiple of a fundamental quantity h nu, which was proportional to E is equal to n times h nu, as given in equation number 6, where h is Planck's constant and n is a positive integer. H nu is the minimum amount of energy that can exchange within the cavity and its wall, and is known as the photon energy. The formula in equation number 25.2 was incorrect. This formula 25.2. So this the equation in the formula in equation number 25.2 was incorrect, and the modified formula according to the Planck's hypothesis for the average energy of a mode is given by the equation, this equation. So you see that this is what Planck suggested. This formula, that is equation number 2, was used by Rayleigh genes, and this formula for the average energy is suggested by Planck's. So this is according to the Planck's hypothesis, that is the discretization of energy concept, because you know that we have E is equal to n times h nu, so n takes integer values, not continuous values. So it means that and h nu is the energy of a photon, as we have stated earlier. So it means that this is an integral multiple of the basic energy. So we have in the numerator, we have the summation sign from n is equal to 0 to infinity, and we have n into h nu into e to the power minus n h nu over kt, and divided by the summation sign, divided by the summation with respect to n from 0 to infinity and e to the power minus n h nu over kt. So if you compare this with the energy over here, you see that here in this formula we have substituted E is equal to n h nu, and we have replaced E with by h nu. So you see that actually we are using the same formula, but here we are using the energy not in the continuous form but in the discrete form. And you see that solving this equation, we have h nu over e to the power h nu over kt minus 1. This is the result that we have that we could obtain. So as h nu goes to 0, the average energy goes to kt. So you can, if you put h nu is equal to 0 in the numerator and in the denominator, and if you differentiate this formula on the right hand side of equation number 7 by h nu, differentiate the numerator by h nu, differentiate the denominator by h nu, and then plug in the value h nu goes to 0, you will get the average value of average value of energy is equal to kt. So this is the classical result. The Planck's radiation formula for spectral energy density thus takes the form. So you see that we are plugging out the value of this energy, average energy, in the previous formula, that is in this formula over here. So we have calculated the average energy, and we have also this PV, which is actually the number of modes per unit volume per unit frequency range. So we are substituting these two values over here, and then we can get the final results using the formula of the Planck's hypothesis. We have rho nu is equal to 8 pi nu square over Cn cube multiplied by h nu over e to the power h nu over kt minus 1, as given in equation number 8. So this agrees very well with the experimental results of the black body radiation curve, provided that H must have this value, that is H is equal to 6.62 into 10 to the power minus 34 joule second. The plot of rho nu versus nu is shown in figure 25.1. The shown curves agree very well with the experimental curves. The average number of photons in each mode is found to be average value of E divided by KT will give you the average number of photon in each mode, where K is the Boltzmann constant. Planck's formula agreed and explained very well the experimental data from black bodies. This was done by introducing a new concept of discrete energy. So you see that the curves of the black body radiations are shown. You see that we have shown at different temperatures, 2000 Kelvin, 2500 Kelvin and 3000 Kelvin, and we have plotted rho nu on the vertical axis and nu on the horizontal axis, and you can see that these are the curves obtained from the black body radiation through experimentation, as well as these are the curves which are also obtained, can also be obtained using the formula given in equation number 8, that is the Planck's radiation formula. So it means that the Planck's radiation formula explains very well the curves of the black body radiation. It means that the hypothesis of the Planck's idea is correct. That is, the discretization of energy concept is correct. Later on, this discrete energy concept became the fundamental concept of energy exchange between the atomic particles, that is from atom to atom or within the atoms, and from molecules and within the molecules, that is within the atom the energy will exchange in the form of discrete, and within the molecules the energy will exchange in discrete fashion. And also the energy from the foreign world to these particles will also take place in discrete form. Now atoms and molecules accept energy in the discrete form and liberate energy in the discrete form. Einstein also based his theory of photoelectric effect on Planck's hypothesis. Dirac founded quantum field theory in 1927, which confirmed the Planck's hypothesis. These explain the significance of Planck's radiation formula. So this is the end of slide number 25.